Hey everyone! Today we're diving into the top 10 takeaways for mastering two-variable statistics in AP Statistics. Whether it's understanding scatterplots, interpreting correlation, or analyzing regression lines, we've got you covered with what you need to excel in this unit. But what's all this learning without a real-world example to tie it all together? That's where our pollinator friends come in. Did you know that 1 in every 3 bites of food you take depends on pollinators? That's right. These little heroes, the ecosystem, from bees and butterflies to bats and birds, are crucial for producing the fruits and vegetables we enjoy every day. Let's take a moment to appreciate the incredible diversity of pollinators found in different parts of the world. In tropical rainforests, colored butterflies flit from flower to flower, while in arid deserts, hummingbirds are the go-to pollinators for cacti and other hardy plants. Even in our backyards, honeybees buzz around, making sure our gardens thrive. Pollinators do more than just beautify our world. They play a vital role in our food system. They help in the fertilization of plants, which leads to the protection of seeds and fruits. Without them, crops like apples, almonds, and tomatoes would become scarce, impacting not only our diets, but also our economy. And it's not just about food. Pollinators support entire ecosystems by aiding in plant reproduction, which in turn provides habitat and food for countless species, including us. Their decline threatens the delicate balance of nature. That's why understanding the relationship between pollinator populations and crop yields is so crucial. In this video, we'll explore data to uncover how these two variables interact and why we should all care about protecting our pollinators. Let's dive in. Let's start with scatterplots. Scatterplots are a fantastic way to visualize the relationship between two variables. Here we are looking at how the number of pollinators like bees and butterflies corresponds with crop yields, essentially how much food our fields produce. Notice how the points tend to move upward from left to right? That suggests a positive relationship. As the number of pollinators increases, so do crop yields. In other words, low pollinators and low yields, and high pollinators and high yields. If we were going to describe the relationship between the number of pollinators and crop yield, we would say that it appears to be roughly linear and moderately strong and positive in its relationship. Now let's explore Least-Squares Regression Line, or LSRL. Later in this video, we will review how to use technology to find the equation of the line. This line provides a clear way to summarize the relationship between the number of pollinators and crop yields. By calculating the LSRL, we can better understand how crop yields change in response to varying numbers of pollinators. The LSRL minimizes the overall distance between the data points and the line itself, helping us find the best fit for our data. This regression line helps us make predictions about crop yields based on the number of pollinators. For example, if we want to predict the crop yield if we have 160,000 pollinators, we can use our equation. When we substitute in 160 for the number of pollinators, we get a predicted yield of 3.358 tons per hectare. Remember that AP Statistics graders will definitely care that you write predicted yield. We don't know what the yield will be, and other factors than the number of pollinators have positive relationships with crop yields, such as weather, soil health, water, and so on. The LSRL is a tool for prediction. It's a vital tool in our analysis, allowing us to see the overall trend in the data. Our third concept that we will discuss is the correlation coefficient, which we denote by the lowercase r. The correlation coefficient will tell us the strength of the linear relationship between the two variables. Mind you, it won't tell us if a linear model is the best fit for the data, but it does tell us the strength and direction of the linear association between the two quantities. Remember that the correlation coefficient can only be between -1 and 1, with -1 being perfectly negatively correlated, all data points lining exactly on the negatively sloped line. 1 being perfectly positively correlated, and again, all of the points lining up exactly on the line, but this time in the positive direction. And 0 being that the two variables have absolutely no correlation. Students often struggle a little bit with values in between. Let's look at some examples. We can use words like weak, relatively weak, moderate, relatively strong, and strong. If you are in doubt if something is strong or relatively strongly associated, I would add the qualifier of relatively, as this softens the language. The correlation between numbers of pollinators and crop yield is 0.968. If asked to interpret the correlation coefficient, we would write the linear association between numbers of pollinators and crop yield is strong and positive. Keep in mind, just because the correlation is close to 1 doesn't mean a linear model is the best model for the data. We will address that issue soon. Now let's tackle causation versus correlation. Just because two variables are correlated doesn't mean one causes the other. We'll explore real life and even some fantastical examples to highlight this crucial distinction. Take pollinators and crop yield, for instance. Scientifically, we know that for apples to form, flowers must be pollinated. So in this case, there is likely some amount of causality between the increase in pollinators and higher crop yields. However, the exact extent of this causal relationship can't be claimed without further experimentation. Other factors like weather, soil quality, water also play important roles, and the impact of pollinators could vary across different crop types. To truly determine causality between pollinators and crop yields, we'd need to conduct experiments and gather specific data. We will talk about experiments in Unit 3, so stay tuned. Let's take a look at some fascinating examples of spurious correlations, relationships that look connected but actually have no cause and effect link. Prepare yourself for some quirky connections. First up, we have correlation between Google searches for avocado toast and the number of associate degrees in science technologies. Now, we all know avocado toast is trendy, but does it really have anything to do with students earning science degrees? Probably not. Yet the data shows they rise together, with a very strong correlation coefficient of R equal to 0.985, a classic case of correlation, not causation. Next, we've got an amusing pair. Lululemon's stock price versus Google searches for Elon Musk. As Lululemon's values soared, so did interest in Elon Musk. Coincidence? Definitely. While both might be making headlines, one doesn't affect the other, yet their trends seem to match. Finally, average SAT scores versus the popularity of the distracted boyfriend meme. You'd think a meme about distraction might hurt SAT scores, but the data says otherwise. The meme was everywhere, yet SAT scores didn't take a nosedive. Again, a clear case of spurious correlation. Just because they line up doesn't mean one caused the other. These examples are fun, but they teach us an important lesson. Just because two things are correlated doesn't mean they're connected in any meaningful way. In statistics, we have to dig deeper to determine if there's a real cause and effect relationship. Otherwise, we'd end up like the distracted boyfriend looking in the wrong direction. The coefficient of determination, or R squared, tells us how much of the variability in y can be explained by variability in x. The value of R squared is literally R, and then you square it. Or you can go the other way around. You can square root R squared to get R. But with this direction, you need to look to see if the slope of your linear model is positive or negative. because our correlation coefficient can be either positive or negative, whereas our coefficient of determination is always positive. In our example of pollinators and crop yields, we have a coefficient of determination of r squared equal to 0.937. This means that 93.7% of the variation in crop yields can be explained by variations in numbers of pollinators. A higher r squared value means a better fit of the model to the data. Let's break down residuals using our pollinator and crop yield data. Remember residuals, the difference between actual values and predicted by our regression model. For example, with 140 pollinators, our model predicted 2.958 tons per hectare, but the actual yield was 2.5 for this particular data point. So the residual is the actual minus predicted, so 2.5 minus 2.958, which gives us a residual of negative 0.4558 tons per hectare. This means our model overpredicted the yield for this data point. Next, we're going to create and look at residual plots. I'll post a link to a video that shows you how to do this on a calculator. For our pollinator and crop yield data, our residual plot looks like this. We can see that there may be a pattern in our residuals. At low pollinator values, there are small residual values, and as pollinators increase, the residuals also increase. This suggests that our linear model possibly isn't capturing the relationship as well as it could, and that we should look for another model type that may fit the data better. Here's where it gets interesting. We could perform a linear transformation of the data and see what the model suggests. In this second example, we took the natural log of both the pollinator data and the crop yield data and ran the LSRL again on this transformed data. This model did a little bit better than our original. There is a little bit less pattern left in the residual plot, and the r squared is a little bit higher. In the third plot, the linearization was done by cube rooting all of the crop yield data and then performing an LSRL with the pollinator data as our explanatory variable and the cubed root of the crop yield data as our response variable. In this one, the r squared is the highest of the three, and there is the least leftover pattern in the residual plot. That makes this third model the best fit for our data out of these three models. Now let's dive into interpreting the slope and y-intercept of our regression line. These two components are key to understanding the relationship between our variables. The slope tells us how much the crop yield changes for every 1 unit increase in the number of pollinators. In our case, the slope is 0.0210 tons per hectare per 1,000 pollinators. This means for every additional 1,000 pollinators, the predicted crop yield increases by 0.0201 tons per hectare. The y-intercept, which is 0.1418 tons per hectare, represents the predicted crop yield when there are no pollinators, 0 pollinators. While it's impossible to have 0 pollinators, we hope, this value gives us a glimpse at what might happen if we were to drastically reduce the number of pollinators. Even without pollinators, there's still some amount of production, but it's significantly lower. By representing the slope and y-intercept separately, we can better understand how the number of pollinators impacts crop yield. Keep in mind, while these calculations fit the data, they're just predictions, not guarantees. Now let's explore two important concepts when using regression models: interpolation and extrapolation. Interpolation is when you use the model to make predictions within the range of existing data. In this case, our data includes pollinator counts from 75,000 to 200,000 pollinators. predicting a crop yield for 100,000 pollinators is interpolation because it's within the range of data. Extrapolation happens when we make predictions outside of the range of data. For example, predicting crop yield for 300,000 pollinators would be extrapolation, as it goes beyond the 200,000 pollinators we have in our data set. Extrapolation can be risky because we're assuming the pattern continues. Without data in that range, we can't be sure that the model still holds. In reality, environmental factors, competition for resources at higher pollinator counts could all cause the trend to change in ways that our linear model doesn't predict. So while interpolation is typically more reliable, we need to be cautious with extrapolation. Predicting for 100,000 pollinators is within our range of data and therefore safer, but predicting for 300,000, that's much less certain. Points are, in a way, a special kind of outlier. They don't just sit far from the rest, but they also have a big influence either on both slope and the position of the regression line, or simply the position of the regression line, leaving slope a little bit unaffected. Watch what happens when we remove this particular influential point from our data set. Notice how the regression line tilts. Notice that the slope is less steep and the y-intercept has raised. This point was pulling the slope to be a bit steeper. The point tilted the line. Let's look at another example. This point is pretty close to the mean of the explanatory variable. Notice that when this point is removed, the slope barely changes, but the y-intercept is higher than without it. This point was pulling the line down, but this point didn't tilt the line. The slope is pretty much the same with or without it. Outliers and influential points don't always need to be removed, but identifying them is key to understanding the reliability of our model. In some cases, they indicate an issue with the data collection process, while in other cases, they might reveal something unexpected about the real-world phenomenon. Now let's put some of our AP Statistics formulas to work. These three formulas are given to you on the AP Statistics formula sheet. The slope of the regression line is equal to the correlation coefficient times the ratio of the standard deviation of the y values over the standard deviation of the x values. The second equation tells us that the mean of the y values is equal to the y-intercept, which is denoted in the equation by the letter a, plus the slope of b times the mean values of the x values. And then finally, our parameters of slope and y-intercept can be put into our regression line equation. Y hat is equal to a plus bx. Let's look at how we could have calculated the LSRL line for our pollinator and crop yield data. For our pollinator data, we have the following values. First, we can calculate the slope of the line using the formula b equals r times the ratio of the standard deviation of y over the standard deviation of x. Our correlation coefficient is 0.968, and then the ratio of our standard deviations is 0.7397 over 35.6149. When we do this calculation, we get a slope of 0.020105, which is what we were given with the technology that created our regression line. Now we can calculate the y-intercept. Y bar is equal to the y-intercept plus our slope times the mean of our x values. So solving for our y-intercept, we get that the mean of our y values minus the slope times the mean of our x values. And then when we substitute in values for those things, we end up getting that our a is equal to 0.142, which is very similar to what the regression equation line found. So then we can substitute in our parameters for our a and our b, our y-intercept, and our slope into the regression line equation, the LSRL equation. Our y hat is equal to 0.142 plus 0.0210 times x, which is very close to the regression line calculated using technology. So by applying these formulas, we built a regression model, an LSRL model, that helps us understand and predict the relationship between pollinators and crop yields, just like the one that was created using technology. That's the power of using AP statistics formulas. You can do it by hand. Knowing how to use your calculator to calculate the LSRL line and how to create a residual plot will be important topics. I'll put a link above to a video that goes through these things rather than to put them directly into this video. Be sure to practice these 10 concepts with real-world data, and you'll be well on your way to acing AP statistics. Thanks for watching. Stay curious, keep questioning, and remember, in statistics, it's not just about cause. It's also how well we can predict what comes next.